Hello, it's Keith here, and this is lesson 3 of my 6809 assembly programming tutorials. This time we're going to be looking at using conditions and branching so that we can check values in registers and generally make the code do different things depending on what our registers contain. Now let's go over to today's code, and we'll have got plenty of examples which we're going to see that are going to show this in action. Now, before we start actually looking at conditions and how to use those, first I'm going to discuss something that's relating to the different kinds of branch that we have available to us on the 6809. Now, we're going to be looking at the difference between BSR, branch to subroutine, and LBSR, long branch to subroutine. Now, branching conditions on most 8-bit processors have a limit of -128 to +127 away from the current running command. Now, you can see here we've branched to this subroutine, which just shows an exclamation mark on the screen there. Not very interesting, but it's just a test. Now, if I enable this piece of code here, which adds 256 dummy bytes into the code, well, now I can't compile. I'm getting an error message that says jump distance too big. You can just about see it down here, jump distance too big. So I can't now compile my code because the distance to subtest is greater than 127 here, so I can't use the regular BSR command. What I can do though is use the LBSR, long branch to subroutine, which can jump much longer distances. Now, the reason we wouldn't want to use it if we can avoid it is because it's a bigger command. It uses more memory, so by using it we're making our program bigger, which will use more memory and be slower, but it does give us the ability to branch to that subroutine that's much further away. Now, these kind of commands, these long and regular versions, exist in the case of a lot of the commands we're going to be looking at today. So first of all, I just wanted to explain the difference between a regular jump and a long jump in the case of the 6809. So that's the difference there. Now next we're going to be discussing what the carry flag is, because the carry flag is going to be relevant in a lot of cases of what we're looking at today. Now, the carry flag is used when an addition or subtraction or a few other commands cause a bit to overflow from a register. The primary use for the carry would be if we were trying to use two registers to effectively simulate a 16-bit number or more, because we can actually combine lots of memory addresses together to do 24-bit, 32-bit or whatever we want. Now let's have a look at this example here. So we're using the A and B registers combined here. Now what we're doing here is, you can see we've loaded A with 1 here, you can see that just here, and we've loaded B with 253, and you can see that over here. Now what we're effectively doing here is we're using the B register as the low part of a pair and the A register as a high part of a pair, and we're effectively going to add to the low part, the B part, and then when the B part overflows, because it goes over 255FF here, that will cause the register B to go to 0, and it will cause the carry flag to be set. You can see these in the middle are the flags represented as letters here. So this C carry flag has been set when B overflowed, and then we can use add with carry ADCA to add a value, in this case value 0, with the carry to the A register here. And so you can see that when this reached 0, the carry was then added to A, and that then became 2 here. And in this case we're adding, and the carry is the amount that needs to be added to the second register, but we can also use it in the other way, and we can actually subtract, and in that case the carry then is treated as a borrow. And you can see here that when the B register went below 0, the carry was set because it was effectively a borrow, and then when we did the second subtract with carry here, that borrow was then taken from the second register, and you can see that went down to 1 here. Now in this case you can see we've added 0 with the second one because we just wanted to add the carry, but we can also add any other value. Of course, in this case I'm going to add a fixed value of 1 here, and you can see here that in this case when the carry was set it went up by 2, and in this case when the carry was set it went down by 2. So as I say, that command ADCA and SBCA will add a fixed value and also anything in the carry to the register. So there we go, that's how we can use the carry. Now in that case we saw a wide variety of registers, and we can do a lot of logical conditions where we will jump to a separate part of the code depending on those flags, and that's what we're going to be doing now. We've got these tests, and each one is going to test a different kind of flag under different circumstances. Okay, so we saw there that if we repeatedly add, then we will effectively cause a carry. And now what we're going to do is we're going to look at how we can branch depending on that, if that carry is set with BCS or if the carry is clear with BCC. Okay, now what we're going to do here is we're going to jump to two routines that will either show a C for carry or an NC for no carry. Okay, now let's just run this and let's see what happens. Okay, so A has started at FE here, and we've added 1 and it's become FF, and then we've added 1 and then the carry has been set because it's gone overflowed to 0, and then we've added 1 again. Now that has caused the carry to clear because the last operation didn't set the carry has reset itself, and so when we ran these conditions here, the carry was not set, the carry was clear, so BCC occurred and we jumped to here and we showed an N and a C. Now what happens if I remove this last add A here? Now I should point out that my subroutines here are protecting the flags, so the monitor ACC function is having no effect on the flags here. Okay, well you can see we skipped that last add and we showed the monitor twice, and in both cases the carry was set. So this time BCS occurred and we jumped to here. Now as in before, these are branches that are limited in the distance that they can jump to. So if I put my DSB here again, and this is going to define 256 bytes. Where are we? Here we are. So if I just put this in here, well, I can't compile again. I've got a jump distance too big once again. But if I put an L in here at the start, well, now I can run my code and my code works again. Now the point I'm making is, again, even though we're just looking at the regular branches here, there are long versions of these branches which will cope with much larger jump distances. So that's how we can use the carry. That's the conditions we're using here. Now there's a lot of other commands that will affect the carry, but we're just looking at this one as an example. It's the conditions and it's the branching conditions that we're looking at today, not the commands that affect the carry here. So there we go, we can use BCC for carry clear, BCS for carry set. It's pretty straightforward. Now that's a common one, but most common of all is going to be equals and not equals. Now in a lot of cases, equals and not equals are more effectively described as 0 and not 0. The equals flag is the 0 flag, so branch if equals will occur if the 0 flag is set. And the way I tend to think about this is when we do a comparison with a compare command, you can see we've got CMP, lots of versions here, is if the register and the value you're comparing, if the difference is 0, then the 0 flag is set and branch if equals will occur. If they're different, then the 0 flag isn't set and then the branch if not equals will occur. Now depending on which register we want to compare, we've got different commands here. So we've got compare A for comparing to the accumulator, the 8-bit accumulator, compare B to compare to B register, compare D to compare to the 16-bit accumulator, compare X to compare to the X register, compare Y, and so on. So we've got a lot of different versions here for comparing a register to and in this case a fixed value here. So we're comparing all of these here, and each of these will set the flags accordingly. Now down here we're doing one final compare just as a test. We're comparing the U register, which is the user stack, and we're comparing either to 55 or 5 in hexadecimal. And then we're going to branch if the Z flag is set equals, and we will show a equal symbol, or if it's not equals, we will show exclamation mark equals, which is the kind of C definition for not equals. Okay, so again here we're going to do these tests. Now let's just fire this up, and first let's just see how each of these flags are set by these comparisons here, which we're not actually branching on, but it's just to show how the flags are set. Now we're going to ignore the carry flag in this case. It's the 0 flag we're really wanting to look at here. So you can see first we've got A equals 1 and B equals 2. So we've compared A to the fixed value 1 here, the immediate value 1. And of course the A is 1, so the 0 flag was set because the difference was 0. So that has caused that 0 flag there. We compared B to 22. Well, B is 2, so that didn't match, so the 0 flag is not set. Then we've compared D, which remember is the combination of A and B, to 0102. Well, A is 1 and B is 2, so that is actually true. So the 0 flag is set again. And then we've compared X to 33. It isn't 33, it's 3, so the 0 flag is not set. And then we've compared the Y register to 4, which it is, so the 0 flag is set. And then we've compared the stack to 4. I don't know what it is, but it's not 4, so the 0 flag has not been set. And then finally we've done these two comparisons, and it's this comparison that's applied here. We've compared U to 5. U is 5, so the 0 flag is set, and branch of equals has occurred, and we've jumped down here and we've shown this equal symbol here. So that's what's occurred there. Now that's the first one, but if I then just rem out this second comparison here, now we're comparing to 55, and that's the one that's going to set the flags that we're testing here. Well, now the U isn't 55, so the zero flag isn't set, and we've jumped from this not equals down to here, and we've shown that exclamation mark equals there. Now, of course, this is all depending on the value of U here. So if I do the comparison to 5 again, and if I change this to 55 up here, well, the comparison is not true again, and that's branched out there. And this is how we can do things like comparisons like your if statement, and also how you can do things like case statements. You can do a sequence of comparisons and a sequence of branches to create a case statement. You've got to remember, of course, that anything you can create in C can be created in assembly, because C compiles down to assembly. So while it may take a little bit more time to write the code in, it might be a bit more difficult, there's nothing that C can do that assembly can't in theory do. It just might not be particularly practical. And as before, we can use the long versions of these if we prefer, and these will branch away much further away if we need to do that. Okay, so that's equals and not equals. That's a very simple one. Now, when we come to compare numbers to see if they're greater than or less than, it's unfortunately a little bit more tricky, and the reason for that is it depends whether we're comparing signed numbers from -32768 to +32767, or unsigned numbers from 0 to 65536, or if you were looking at 8-bit, -128 to +127, or 0 to 255, of course. So here we're going to load a value in that is going to be potentially ambiguous, hexadecimal 7000 here, and we're going to do some comparisons here. And this is going to depend on whether this is a signed number we're comparing to or an unsigned number. Now, first of all, we're going to compare to an unsigned number, which is going to mean that this register D could go up to 65535. So in this case, we're going to compare to each of these values, and we're going to do a branch using these unsigned branches. So branch if higher than the same, branch if lower than same, or branch if lower. And we're going to show either a greater than symbol or a less than symbol. Now, less than same and higher than same, we don't have an equal symbol we're showing here, but it's just to show the various range of options we've got here. Okay, so let's fire this up and let's see what happens. So we've loaded D with 7000 here, and we're comparing to 6000 in hexadecimal, and of course 6000 is less than 7000, so if branch if higher has occurred, and it's shown the greater than symbol. Now if I change this to 6000, well, what will happen now? Well, we've shown the greater than symbol again. Now what's actually happened here is that this higher than same has occurred. If I change the order of these, if I put this less than same in front of that, well, now we've shown a less than symbol because this less than same has occurred first before this higher than same. So in this case, the order has mattered. Now, of course, you could have, instead of using these higher than sames, you could have done a branch if equals as well. That would be another option, but that's not what we've done here. We've used this higher than same or less than same instead. Okay, so that's what happens if we compare to 6000. What happens if we compare to a higher number, 7800? Well, of course, our 7000 is now less than 7800, so the branch has gone to branch if lower than or same here, and we've shown the less than symbol here, and that makes a lot of sense. Now the tricky one is going to be if we compare to hexadecimal 8000. Now why is it tricky? Well, hexadecimal 8000 is 32768 if we are using unsigned numbers. However, if we're using signed numbers, it's minus 32768 because of the way that hexadecimal numbers work. So if we use the wrong kind of command to compare, we will be comparing the wrong number. Let me just show you what this means. So we're comparing to hexadecimal 8000 here, and 7000 is of course less than hexadecimal 8000. Right, well, so we've shown a less than symbol there. Well, that makes sense. Well, what about if I put in here minus 32768? Well, hexadecimal 7000 is 28,672, which is of course greater than a negative number, but it's actually showing as less than because we're using conditions that are treating these as unsigned numbers, and so we've actually got the wrong result there. Now, if we want to compare to negative numbers and we're treating the D register as a negative number in this case, we need to use different conditions here. So if we just enable the signed tests here, and if we go down here, and we've got these alternate versions which are for signed numbers, BGT, which is branch if greater than, BGE, branch if greater than equals, BLT, which is nothing to do with lettuce and tomatoes, that is branch if less than, or BLE, which is branch if less than or equal. So these are the alternate versions, and these are the signed versions of these. Now if we compile this again, you can see now that we're testing comparing hexadecimal 7000 to hexadecimal 8000, which is effectively minus 32768 here. So of course hexadecimal 7000 is greater than minus 32768, even though it looks like it might be lower if it was an unsigned number. Now of course this will work if we use lower numbers as well. If I just disable that and compile this one, well, now hexadecimal 7000 is greater than hexadecimal 6000, so we've shown a greater than symbol here. But if we do hexadecimal 7800, well, of course that's less than. So these are the equivalent versions of the comparisons for signed numbers for these ones here, and it just depends on how we're treating our registers, whether we're considering the numbers in them to be signed or unsigned. That defines which ones of those versions we want to use. So that's how we can do comparisons and see which number is greater than or less than. We do have some other comparisons which are quite handy for various purposes. Now we have a function that's quite handy, which is the negative flag. Now this effectively tests the top bit of a register, because if you remember, of course, minus negative numbers, the top bit will always be set to 1 to represent the negative number, and it will be 0 for a positive number if the register is being treated as signed. And so you can see we've loaded various values here, and if you think about it, a value like FF will have the top bit as 1, so the N flag has been set. This is got the top bit as 0, so the negative flag is clear. These have all got the top bit of 0, so the negative flag is clear. These have all got the top bit set, so the negative flag has been set here. And these are, of course, all 8-bit numbers, but the same is true if we use 16-bit numbers. Here, this one has the top bit set here, so the N flag is set. And this one has the top bit clear, so the N flag has been cleared here. And we can have a condition that happens if the flag is negative or not. So we've got branch if minus here, and we've got branch if plus here, and we can show a plus or a minus accordingly. So you can see here that we, in this case, we were testing, and we tested against 100 here. And so you can see here we've loaded 100 in hexadecimal, which is of course positive. So the N flag is clear, and we've branched and shown the plus. But if I just run this line out, then of course the negative flag has been set here, and that means we've branched and shown the minus. Now of course, as I said before, it all depends how we're treating the numbers. If we are treating the numbers as unsigned and we use these, then they're not going to work very well. If I do just C000 here, well, that is actually going to set the N flag because the top bit is set, so that cannot be used in a signed value there. But this does have a sort of side benefit that in some cases people use the negative flag to quickly test the top bit of a register or a value, because it's quicker than doing some kind of bit masking to check it. So that's a quite handy trick that people often do, using that negative flag as a quick way of testing whether the top bit of something was set. So there we go. That's the negative flag. Now this does follow into something else that's quite important, and this is overflow. Now if you think about it, there's a big problem with our signed numbers, because of course when we're using a signed number, half of the range 8000 onwards is negative and all the other numbers are positive. Now the problem occurs is what happens if we're very close to that boundary and we keep incrementing or decrementing. We're going to end up overflowing and flipping from a positive number to a negative number, or a negative number to a positive number. Now I often give this example because it's quite funny. Imagine if you had a bank account and you owed minus £32,700, and then you borrowed another £500. Well, it would flip to a positive number, and you'd actually end up with a lot of money when you actually had none at all. Now of course that's an absurd example. No one would use an 8-bit processor for banking, certainly not today. But the point I'm making is that you can't have your numbers, the signs of your numbers, flipping over accidentally. So that's what we're going to be looking at here, and we're going to be looking at this, and it's called the overflow flag. We have BVS, branch if overflow set. V is overflow in this case. BVC, branch if overflow clear. And overflow occurs when a positive number changes to a negative number, or a negative number changes to a positive number. So let's have a look at that here. Okay, so here we've got the accumulator here. We've loaded it with 7D, which is a positive number. And then we've added 1 to 7F, which is also a positive number, 127. Then we've added another 1. Now that has accidentally turned it into a negative number. So you can see this has become minus 128, and the V flag has been set. Now our branch if overflow is set has occurred, and we've shown a V here. So we've detected that error, and we've branched out to maybe fix it somehow. So we've been able to detect that. Now if I put another link in, well, the overflow flag will be cleared, because changing from hexadecimal 80, which is minus 128, to adding 1, we become minus 127. That's a typo, I'm sorry there. It should be minus 127. So actually, at this point, the overflow has cleared because that looks like a legitimate mathematical result there. Now, in that example, we used 8-bit numbers, but we can do the same with 16-bit numbers. The overflow flag will also be set. So here we've loaded a large 16-bit number, and we're repeatedly adding 1. Well, once again, we've gone over from minus 32767 to plus 32768, and that has caused the overflow flag to be set. Now, in that case, I just need to rem out my last command here and just run again. And you can see the overflow flag has been set by this overflow here between the two values. Now in that case we've done an addition, but the overflow will occur with a subtraction as well. So if we just change these to sub, well, you can see here that we've repeatedly subtracted, and that has caused an overflow here, and that overflow has set the V flag, and we've branched again. So overflows occur when a positive switches to a negative, or a negative switches to a positive without good reason. Now if it occurred because we were repeatedly subtracting from the value 2, for example, well, that's going to be legitimate, because that's not caused any data loss. That's just because we've gone below 0. So you can see here that we've gone below 0, but the overflow flag was never set. It's only when a mistake occurred that the sign flipped that the overflow flag is set. So there we go. Those are quite interesting. Those are ones I didn't really understand when I started doing assembly programming, but they are very logical, and you can imagine there would be good uses for them. Now we are just going to cover some rather strange ones now. There's branch always, which will always branch, and branch never, which will never occur at all. Now, I think these are kind of quirks of the instruction set, but basically branch is branch always, and BRN is branch never. So branch never will never occur, and branch always is just a branch, basically. So if we just run these, of course, we've branched to this B here. We didn't show the N. We never will show the N. It's impossible to occur. The only thing I think could be useful with this if you were using self-modifying code, which is where you reprogram parts of your code automatically. For example, if you had a game which had a 2-player mode and you wanted to disable the 2-player function in the main loop, you could change the branch to the second player function from a BRA to a BRN, and that would effectively disable it, and it would mean you didn't have to waste any processing power doing comparisons to check any settings values or anything. So I can imagine it being useful for that, but it's a bit of a strange one, and as I say, while branch always is effectively our regular branch, branch never will never occur. So there we go. It's just a thing that's there and possibly isn't so much use to us, but it's there anyway, and it's worth knowing about. So there we go. We've covered a large number of branches today, and we've had a look at some condition codes and some flags and things. So now hopefully you will be in a position to be able to write sort of logical loops within your code where you're maybe testing joystick directions and moving an object around the screen and checking if they've got to the edges of the screen and increasing high scores and things like that. It's all, you know, essential, and it's one of the fundamental building blocks of writing a program, of course. So there we go. I hope you've enjoyed this. I hope you found it interesting. Of course, you can download all the source code from my website and the build scripts and things, so hopefully you'll be able to try these out at home if you want. But if you've enjoyed this, please like and subscribe. If you like the videos, then YouTube will recommend them to other people, because they count how many people like videos and decide who to recommend to based on that. And if you subscribe to the video as well, it just generally increases my motivation to sit around here making more videos, because it takes a lot of time to research them, write the documentation and things. But whatever you do, I wish you all the best with your 6, 8, or 9 programming. Thanks for watching today, and goodbye.